Welcome to my channel. Today we are going to solve the FIR low pass filter design problem using Kaiser window. Okay, so we solved FIR low pass filter problem using the various method, Fourier series method, then various windowing technique and frequency sampling method we solved. Okay, but see here the specification is different. So here you see alpha p, okay, pass band ripple is less than or equal to 0.1 dB. Stop band attenuation, it is greater than or equal to 44 dB. Omega p, pass band frequency 20 radians per second. Omega s, stop band frequency 30 radians per second. Omega sf, it's a sampling frequency 100 radians per second. Okay, so using Kaiser window. So we are going to solve this problem in Kaiser window. So in previous video, we discussed that is the steps to be followed in order to design the FIR filter in Kaiser window. We detailedly discussed. Okay, so if you should know the procedure, okay, and formulas. So you see, this is the procedure in order to design the FIR filter using Kaiser window. So all these formulas you should know, then only you have to calculate this problem in a very easy method. Okay, so here we are going to see the thing. So first from the given specification, so first we have to find some data. So what all the data mean? The transition bandwidth, okay, B. Capital B is nothing but the transition band. It is nothing but it's a difference between stop band frequency and pass band frequency. So here, what is the stop band frequency? 30 radians. What is the pass band? 20 radians. So 30 minus 20, 10 radians per second. Okay. And the next one, using this stop band and pass band frequency, we have to calculate the cutoff frequency. So what is the cutoff frequency? The cutoff frequency is nothing but it's average of the pass band and stop band frequency. Omega p plus omega s divided by 2. So 20 plus 30 divided by 2. So 50 by 2, 25 radians per second. Okay. So here you see the frequency and transition bandwidth is in the unit radians per second. Okay. So we needed omega c, the cutoff frequency in radians. Okay. Not radians per second. So in order to convert the omega c in radian, you just multiply omega c in radians per second with the time t. Okay. So here the sampling time t is nothing but 2 pi by omega sf. Okay. So what is omega c? Omega c in radian per second is 25 into 2 pi divided by omega sf. So what is the sampling frequency? 100 radians. So just substitute here. So 25, 2 pi by 100. So 25, 100 if you are cancelling, here 4, then 2, 4 if you are cancelling, we can get the answer is pi by 2 radians. So the cutoff frequency in radians is pi by 2. Okay, that is 90 degree, pi by 2. Okay, so we calculated the transition bandwidth and cutoff frequency in radians. Okay, this is the first thing. So then we are moving to the design. So the first step in the Kaiser windowing technique is first we have to determine HD of n, okay, using the Fourier series method for an ideal frequency response. So you already know the frequency response of low pass filter, the HD of e power j omega is 1, okay, for the modulus of omega less than or equal to omega c. So here, what is omega c? Omega c we calculated as pi by 2. Okay, so in previous problem in Fourier series method and in various windowing technique, so the given specification is in this format. Okay, but here in this Kaiser windowing problem, so the design specification is not given like this. So the data given is pass band ripple, stop band ripple, pass band frequency and stop band frequency. So using this frequency, you just find the cutoff frequency. Then in this structure, you just write the find the ideal frequency response. Okay. So the HD of e power j omega is 1 for the modulus of omega less than or equal to pi by 2, 0 otherwise. Okay. So using this HD of e power j omega, we have to determine small HD of n. Okay. Desired impulse response. So you know the formula 1 by 2 pi integration over minus pi to pi hd of e power j omega into e power j omega n d omega. So in this, we have to substitute the hd of e power j omega value. What is hd of e power j omega? It is 1 for the modulus of omega less than or equal to pi by 2. So what is the meaning of this? From minus pi by 2 to plus pi by 2, the hd of e power j omega is 1. Okay, so 1 by 2 pi integration over minus pi by 2 to pi by 2, 1 into e power j omega and d omega. So this integration is similar to the method we discussed in ordinary Fourier series method as well as the various windowing technique method. Okay, so in that you just integrate it. So if you are integrating e power j omega n with respect to omega, we can get e power j omega n by j into n. Okay, with the limit minus pi by 2 to pi by 2. So here you substitute the upper limit and lower limit instead of omega. So we can get 1 by 2 pi e power j n pi by 2 minus of e power minus j n pi by 2 divided by j n. Okay, so in that, that is this 2 you give inside the bracket and n you take it outside. So 1 by pi n this. Okay, so you see this value is in the structure of e power j theta minus e power minus j theta divided by 2j. Okay, so what is that? E power j theta minus e power minus j theta divided by 2j, it is said to be the sine theta. So we can write sine theta in the place of theta, which one is available? N pi by 2. So the answer is the hd of n is equal to sine n pi by 2 divided by pi n. Okay, for the time n is between minus infinity to infinity. So the desired impulse response we calculated. This is using the previous method, Fourier series. Okay, and various windowing technique we discussed. The same procedure you just follow. Okay, then for that hd of n, so we have to find the various values of hd of n. Okay, so now that is the order of the filter, capital N, you didn't know. Okay, that's why. So in that step, we can't find this hd of n value. Okay, so after the step number 5 only, we have to calculate this. Okay, then the next step is we have to choose del. So del value, del is nothing but it's a minimum value of del 1 and del 2. Okay, so what is del 1? 10 to the power minus 0.05 alpha s. Okay, so here in our problem, the stop band attenuation is given. What is alpha s? Alpha s is 44 dB. Alpha p is 0.1 dB. Okay, so you just substitute alpha s value here. So you see, so 10 to the power minus 0.05 into 44. Okay, you just find the answer. This is del 1. Similarly, del 2 equal to, the formula, 10 to the power minus 0.05 alpha p minus 1 by 10 to the power minus 0.05 alpha p plus 1. Okay, so where alpha p is a 0.1. Okay, so in problem, the alpha p is given as 0.1 dB. So you just substitute the value and you find the thing. The answer is 5.7563 into 10 to the power minus 3. So out of this del 1 and del 2, which one is lowest value? In del 1 and del 2 is a lowest value. So that del 1 is a del. Okay, so therefore the del is equal to minimum of del 1 and del 2. So you just write the del 2 value. Okay, it's a second step. Then the third step, we have to find alpha s. Okay, so the alpha s, alpha s is nothing but minus 20 into log of del. Okay, so minus 20 into log of this 5.7563 into 10 to the power minus 3. So if you are calculating, we can get the answer as 44.797 dB. Okay, so the stop band, minimum stop band attenuation we calculated. Okay, minimum stop band attenuation. In our problem itself, alpha s is given, it's a 44 dB. Okay, this is the minimum stop band attenuation we have to calculate using the formula minus 20 log of del. Okay, so once you calculated alpha s, the next step is we have to determine the parameter alpha. Okay, so what is alpha means? This alpha is having either any one of this three value depending upon the alpha s value. Okay, if alpha s less than 21 means 0. In between 21 to 50 means we have to use this formula. If greater than 50 means we have to use this formula. Okay, so here you see what is alpha value, alpha s value 44.79. So 44.79 means it is under the category of second one. Alpha s lies between 21 to 50. Okay, since 44.79 lies in this range. Okay, so that's why we have to select this second formula. So the alpha value equal to 0.5842 alpha s minus 21 to the power 0.4 plus 0.07886 alpha s minus 21. Okay, so here we have to substitute the alpha s value and we have to find the alpha. Okay, so you see, so therefore the alpha equal to 0.5842. You just write the formula. Then here you see alpha s value we are substituting, it's a 44. Okay, so you just substitute. So after substituting, we have to calculate the alpha is 3.9524. Okay, so once you calculated this alpha, okay, next we have to find the parameter d. Okay, so why we are calculating this alpha, d, and so many things means we have to find the order of the filter. This order n is depending upon the parameter d. So the parameter d is depending upon the value of alpha. So that's why we are calculating in reverse. Okay. So here the parameter d is having the two things. If alpha is less than 21, this is the answer. If alpha is greater than 21, this is the answer. So now we are having alpha s is equal to, what is the answer for alpha s? 44. Okay, so that's why the alpha s is greater than 21. This condition is satisfied. So we have to calculate the d value using this formula. So alpha s minus 7.95 divided by 14.36. So you just substitute the alpha s value. Alpha s value in our problem, it is given as 44. You just substitute and find the answer 2.566. Okay. So once you calculated d, the next step is we have to find the order of the filter, capital N. Okay. So what is the order? Order formula is in previous problems. Okay. So in our FIR Hamming window problem, the problem itself, the capital N value is given. Okay. You just solve design low pass filter for capital N equal to 11, for capital N equal to 7 or 9 will be given, but here the order is not given. So we have to find the order. So N is greater than or equal to omega SF d by b plus 1. So what is omega SF? In our problem itself, it is given 100 radians per second into d. D just now we calculated 2.566 divided by b. The transition bandwidth we calculated in our problem in first thing. The transition bandwidth is nothing but omega s minus omega p. Okay, it is 10 radians per second. So you just substitute all this value in our n formula plus 1. So if you are substituting, we can get 26.66. Okay, so always the order should be in odd number. So the 26.66 we can round off to the next integer 27. So here we are going to design the filter of order 27. Okay, so n is calculated. So once the n is calculated, you just find the HD of n value. Okay, HD of n value for various n. Okay, so this Kaiser window, all windowing sequence, it obeys the property, symmetry property. Okay, about the 0 axis, the windowing sequence, it should have the same value. Okay, that is h of 1 and the windowing sequence w of 1 and w of minus 1 is equal. Similarly, w of 2, w of minus 2 is also equal. Similarly, our impulse response is also symmetric about n equal to 0. Okay, so that's why for capital n equal to 27 means, so the n ranges from minus of n minus 1 by 2 to plus n minus 1 by 2. That means minus of n minus 1 by 2 minus 13 to plus 13 we have to calculate. Okay, and you know this response is symmetric. Okay, so that's why for n equal to 0. Okay, so you just substitute n equal to 0 in this HD of 0. Okay, put n equal to 0 and you just find the answer. It is 0.5. Similarly, you put n equal to 1, 0.318. For n equal to 1, n equal to -1, the same answer will come. Similarly, for n equal to 2, 0, n equal to 3 minus 0.106. Okay, and that is in this HD of n, you just substitute the n value. Here one n, here one n is available. You just substitute the n value and find out the answer. Okay, and make a table. So for n equal to 0 to 13, we are calculated. Okay. Then the next step is to, so the desired impulse response calculator. So the next step is to, we have to compute the windowing sequence. Okay, so here we are going to use the Kaiser window. Already you know the formula for Kaiser window. The Wk of n is equal to I naught of, okay, where I naught is a function. Okay, one function. I naught of alpha into square root of 1 minus 2n by n minus 1 the whole square divided by I naught of alpha for modulus of n less than or equal to n minus 1 by 2, 0 otherwise. Okay, and where this I naught of alpha is 10.8468. That is I naught of alpha means this I naught is in order to calculate this I naught function, you know this is the I naught function. The I naught of x is equal to 1 plus summation k equal to 1 to infinity 1 by k factorial x by to the power k to the whole square. This is the function I naught of x. Okay, so if you are expanding this, we can get 1 plus 0.25 x squared by 1 factorial the whole square plus 0.25 x squared the whole square divided by 2 factorial the whole square plus 0.25 x squared to the whole power 3 divided by 3 factorial whole squared plus etc. Okay, the series is having infinite. So for calculation, you just do for some 7. Okay, 7 term. You just find the 7 term and you add it. We can get the I naught of x value. Okay, so here for one sample, I am calculating. That is I naught of alpha value. Here I am calculating. What is alpha? Alpha is 3 point. See the alpha value. Okay, alpha is 3.9524. Okay, so here we want I naught of alpha value in order to find the windowing sequence. So the I naught of alpha, I naught of 3.9524 is calculated by, you just substitute in the place of x. Okay, x is here the variable, instead of x 3.9522. Okay, so you just substitute and you make a calculation. Okay, so up to 7 term you just calculate. So the answer is 10.8468. Okay, so I naught of alpha equal to 10.8468. So once you calculated, we have to calculate the various windowing sequence, wk of 0 to w up to wk of 13. Okay, since the capital n is equal to 27. So capital N is 27 means we have to calculate the windowing sequence for minus 13 to plus 13. Okay, already you know windowing sequence are symmetric. That is w of k, wk of 1 and wk of minus 1 is equal. 2 minus 2 equal, 3 minus 3 equal, 4 minus 4 equal. Okay, all these things. So, so first we are calculating the wk of 0. Okay, so what is wk of 0? So the wk of 0 means you just substitute n equal to 0 in this formula. So you just substitute n 0. So this term 0, 1. So I naught of alpha. I naught of alpha divided by I naught of alpha. So wk of 0 is I naught of alpha divided by I naught of alpha. So cancelling, we can get 1. Okay, all windowing sequence is having the answer 1 at n equal to 0. Either it is a rectangular window, hamming any window at n equal to 0, that window is having the answer maximum value 1. Okay, then wk of 1. What is wk of 1? So we have to substitute in this formula, instead of this small n, we have to substitute 1. And capital N is 27. So you just substitute. If we are substituting, we can get I naught of alpha into square root of 1 minus 2 divided by 26 the whole square. Okay, so if you are taking square root all these things, we can get I naught of 3.9406 divided by I naught of alpha. Already I naught of alpha we calculated the answer 10.8468. Okay, and again you just calculate this I naught of 3.9406. You have to calculate using, okay, using this series. You just calculate separately and you just divide it. We can get 0.9899. Okay, so this calculation is somewhat that is okay, similar to, okay, you just expand this expansion for up to 6 or 7 term. You just find the I naught of value, then you divide, the answer is 0.9899. Similarly, WK of 2 and K of minus 2 is calculated by 0.9603. Similarly, WK of 3, 0.9124, WK of 4, 0.848, WK of 5, 0.7546. Okay, the windowing sequence, you see the window sequence value decreases. In center, at n equal to 0, the sequence is having maximum value 1. Okay, whenever this n value increases, the value, okay, it is decreases. All window sequence is having like that only. So for WK of 8, 0.49, WK of 9, 0.39, WK of 10, 0.3, WK of 11, 0.22, WK of 12, 0.15, WK of 13, 0.09. Okay, so we calculated the 27 windowing sequence. Okay, so once you calculated the windowing sequence, what is the next step? We have to compute the modified impulse response. That is, the H of n is nothing but we have to multiply the windowing sequence with the corresponding desired impulse response. Okay, so you see, for the n is equal to 0 to 13. Okay, HD of n is this, and you just multiply the WK of n, so we can get H of n. So H of n is HD of n multiplied with WK. So here you just make another one column, WK value also you just write and you multiply. So we can get the answer, you see, the H of n is 0.5 when n is equal to 0. When n equal to 1, 0.31479. Then 0 minus 0.0967, then again 0, 0.4804, again 0, minus 0.0268, 0, 0.014. Okay, so you see this coefficient, when n increases, the value decreases. Okay, so we calculated. So once you calculated the H of n value, you just take the Z transform for this H of n, and we have to multiply it with Z power minus of n minus 1 by 2, we can get the realizable filter. So the transfer function H of Z is calculated by Z power minus of n minus 1 by 2 into small h of 0 plus 2 into summation n equal to 0 to n minus 1 by 2 H of n Z power minus n plus Z power plus n. So you just substitute this various H of n value here, we can get the transfer function. Okay, so here n minus 1 by 2 is 13. So Z power minus 13 into H of 0 plus 2 into n equal to 0 to 13 this. So you just expand it, you just substitute this various this H of n value, we can get the transfer function. Okay, so this is the design of FIR filter using the Kaiser window. Okay, so when compared to the remaining windowing technique, so this windowing technique becomes somewhat complex. Okay, so this is the procedure in order to solve the FIR filter using Kaiser window. Okay, so using this Kaiser window, we can solve bandpass filter, bandstop, and so on. Okay, so thanks for watching my channel, and please subscribe my channel for more videos and press the bell notification button. Then only you can get notification once I am posting the video. Okay, so if you want to learn the lecture videos related with this subject digital signal processing or discrete time signal processing. In my channel, in the name of this DTSP or DSP, the playlist is that. In that playlist, all lecture videos are available in order from unit 1 to 3. Okay, so you can learn. I will give the link in the description box. You can refer it. Okay, so thank you. We will meet in the next video.